Today we start our discussion of concepts in chapters 3, including resistors in parallel and series and the voltage and current divider. We've already briefly discussed series and parallel, but let's give it a more formal definition. When two elements connected a single node pair, they are said to be in series. A common mistake students make is assuming that any number of elements that meet are in series. No, only when exactly two elements meet at the node, such as here, R1 and R2 are in series. Only because there's only two. Because elements that are in series have the same current, which means the current would flow from R1 to R2. If I added a third resistor at the same node, that would not be true, and they would not be in series. So conversely, same current means series, or two elements meet at a node, they are in series. When elements are in series, we say that the equivalent resistance seen for those resistors is the sum of the individual resistances. Therefore, the equivalent resistance of a network of resistors in series is always larger than the individual resistor. Let me show you a simple example of what I mean. Here we have three resistors. Let's say a 2 ohm, a 3 ohm, and a 5 ohm resistor. They're definitely in series because only two of them meet at each node. The equivalent resistance seen by RAB would then be 2 plus 3 plus 5, or 10 ohms. Our next definition is parallel. When two or more elements connected a single node pair, they are said to be in parallel. Elements in parallel have the same voltage. So the key to parallel is that the elements have to be connected on both sides, either top and bottom or left and right, but they have to be connected on both sides, and they must have the same voltage. So elements that share the same voltage or elements that share the same node pair are said to be in parallel. The equivalent resistance for parallel resistors is the reciprocal of the sum of the individual conductances. Therefore, the equivalent resistance is always smaller than the smallest individual resistance. Many times in this course, you will see me use this special case for finding equivalent resistance for parallel resistors, which is the product over the sum. But let's look at an example. What if I have an 18 ohm, a 9 ohm, and a 6 ohm resistor in parallel? And I call the resistance between them RAB. The resistor that RAB would see would be 1 over 18 plus 1 over 9 plus 1 over 6, which is equal to 4 ohms. And let's do an example using the product and the sum. Let's say I have a 20 ohm resistor in parallel with a 5 ohm resistor, and I want to know the equivalent resistance seen. So I would have 20 ohms and 5 ohms. So RAB would be equal to 20 times 5 over 20 plus 5, which is also 4 ohms. This concludes our review of how to find parallel and series equivalent resistance. So now let's look at some concept questions related to resistance, power, voltage, and current. In the following circuit, we have a 75 watt and a 50 watt light bulb, and they are placed in parallel across a voltage source. Which of the following statements is true? One of the first things I want to show you is that we can have a battery symbol that represents a voltage source. You will see this when you do the multi-sim simulations for some of your pre-lab circuits, that this battery symbol is equivalent to having a voltage source where the longer line represents the positive and the shorter line represents the negative. Now, since all three of these elements are in parallel, parallel means same voltage. So since I know the power for each of the bulbs, I can find the current since I know that they have the same voltage. So remember, the voltage for bulb A is equal to the voltage for bulb B. However, for that top bulb, I know that 75 divided by the current through that bulb has to equal 50 divided by the current through the second bulb. Okay, where this current would be IB and this current would be IA. So if I solve this equation for IA, I have that IA is equal to 75 over 50 times IB, which means that IA has a larger current, or the 75 watt bulb has a larger current. Notice that power is directly proportional to current, which means the bulb that had the larger wattage had the larger current, since both of them have the same voltage. Now for the second concept question, the question says, if I have identical resistors in a parallel circuit between points P and Q, the total resistance between points P and Q as I continue to add resistors would increase, decrease, or remain the same. Now, since we just talked about the fact that parallel equivalence is going to be smaller than the smallest resistor in the parallel network, that means the more resistors I add, the smaller the equivalent resistance will become. So the equivalent resistance will decrease. So now let's find the equivalent resistance of a more complicated network. So for the following network, we want to find RAB, the equivalent resistance seen from terminals A and B. The strategy is to work from the outside in, or in this case, from the right to the left side towards A and B. So the first thing you do is find some elements that are in either parallel or series. We actually have two sets of resistors that are in parallel. The 20 ohm and 5 ohm resistor at the top are in parallel, and the 18 and 9 ohm resistor at the bottom are in parallel. So now I redraw the circuit. I have the original 8 ohm resistor, and now I have the resistor that results from 20 in parallel with 5, which is 4 ohms. Then on the right over here, I have a 1 ohm resistor. I still have that 20 ohm resistor that's diagonal, the 2 ohm resistor here. Here's terminal B, and then 18 in parallel with 9, which is 6 ohms. So now I want to find some resistors that are in series or parallel. I actually only have 2. This 4 and 1 are in series. So 4 plus 1 gives me a 5 ohm resistor. And now I copy everything else down. So once again, I copy down the 8 ohm resistor. I copy down the 20 ohm resistor. I copy down the 2 ohm resistor. And I copy the 6 ohm resistor. So now what do I have in parallel or series? Well, I have this 5 ohm resistor and this 20 ohm resistor. They're connected on the top and on the bottom, so they are definitely in parallel. So once again, I have 20 in parallel with 5. 20 in parallel with 5 yields 4 ohms again. And then I copy down the rest of the original network. Here's my 8 ohm resistor. Here's the 6 ohm resistor. And here's the 2 ohm resistor. So recall, this was a result of 20 in parallel with 5. So now what do we have in series? I have this 4 ohm and this 2 ohm resistor in series. So I will put those together to yield 6 ohms. So I have at terminal A an 8 ohm resistor. At terminal B I have the wire. And then I have the 6 ohm resistor here, and the 6 ohm resistor here. That's a result of 4 plus 2. My next step, I have an 8 ohm resistor and 6 in parallel with 6 yields 3 ohms. So finally, RAB is equal to 8 plus 3, which equals 11 ohms. Now let's talk about the voltage divider, which is based upon Kirchhoff's voltage law. The voltage divider is used to calculate the voltage across resistors when the voltage is supplied from a single source. Notice you don't necessarily have to have a voltage source, but you do have to know the voltage across a set of series resistors in order to use the voltage divider. The voltage divider is based upon KVL, and we can see that by looking at this equation here. The sum of the voltages around the loop is negative V plus V1 plus V2 plus V3 equals 0. So if we define that clockwise current I, then we have negative V plus IR1 plus IR2 plus IR3 equals 0. So when we solve for I, we see that I is equal to the voltage source divided by the sum of the 3 series resistors. So if I only wanted to know the voltage across, let's say, the third resistor, that would be I times R3, which yields the equation, the voltage source times the resistor you want on top, R3, divided by the sum of the resistors. So from this, the voltage divider rule is the voltage across resistor N is Rn divided by the series sum of the 3 resistors times the voltage source. When you're done finding the voltage for all of the resistors, you can actually use KVL to check your work. Let's look at an example of this. I have a 15 volt source, and that is the voltage across 3 resistors, a 2 ohm, a 3 ohm, and a 5 ohm resistor. I'll call the voltage across the 2 ohm V1, the voltage across the 3 ohm V2, and the voltage across the 5 ohm V3. So V1 would be equal to 2 over 2 plus 3 plus 5 times 15, which equals 3 volts. V2 is across the 3 ohm resistor, so 3 is in the numerator, divided by 2 plus 3 plus 5 times 15, which is equal to 4.5 volts. V3 is the voltage across the 5 ohm resistor, so that's 5 divided by 2 plus 3 plus 5 times 15, and that equals 7.5 volts. So we use KVL to check our work. Since 3 plus 4.5 plus 7.5 does indeed add up to 15, which was the voltage source, the solution works. The current divider is based upon Kirchhoff's current law, and it is based upon a current source that feeds parallel resistors. You don't necessarily have to have a current source, but you do have to know the current that gets divided between resistors in parallel. So remember, voltage divider is for series resistors with a sourcing voltage. Current divider is for parallel resistors with a sourcing current. Let's use KCL to see why the current divider works. So if I do KCL at this top node, I have that the current coming in, negative I, is equal to the current coming out, I1 plus I2 plus I3. Now if I define this top node to be the voltage V, then V is equal to the negative I plus V over R1 plus V over R2 plus V over R3 equals 0. And I can solve for V, and I see that V is equal to I over G1 plus G2 plus G3. Remember, G1 is 1 over R1, G2 is 1 over R2, and so on. So if I want to find I3 would be equal to the current through R3, G3 over G1 plus G2 plus G3. What this yields is that if I want the current through a particular resistor, it's the conductance for that resistor divided by the sum of all of the conductances. The current divider rule can also be defined in terms of equivalent resistance, where the numerator is the equivalent parallel resistance seen by the resistors divided by the resistor for the one you want the current through times the source current. Let's look at an example. Assume I have a 36 amp current source and its source is 3 parallel resistors, an 18 ohm, a 9 ohm, and a 6 ohm. I would call the current through the 18 ohm I1, the current through the 9 ohm I2, and the current through the 6 ohm I3. So I1 is going to equal the parallel combination of the 3 resistors 18, 9, and 6 divided by 18 for the resistor I want times the source current, which is 36, which equals 3 over 18 times 36, or 1/6 times 36, which is 6 amps. I2 is equal to 18 and parallel with 9 and parallel with 6 divided by 9 times 36, which is 3 over 9 times 36, which equals 12 amps. I3 is equal to 18 and parallel with 9 and parallel with 6 divided by 6 times 36, which equals 3 over 6 times 36, which equals 18 amps. And you can always check your work by using KCL. So what we should find is that I1 plus I2 plus I3 should equal the source current, which is 36. So 6 plus 12 plus 18 equals 36. So our solution does indeed check. Okay, let's try one more voltage and current divider example. For the above circuit, we have a current divider relationship with IC to find the current through the 3 and 6 ohm resistors. So if we look here, IC is the source and current that IC is the source and current that divides between the 6 ohm and the 3 ohm resistor. So if I was going to write a relationship in order to find the current through the 3 ohm and 6 ohm resistors using IC, that equation would be the current through the 6 ohm resistor is equal to 6 in parallel with 3 divided by 6 times IC, which is 2 over 6 IC, or 1/3 IC. For the current through the 3 ohm resistor, that would be 6 in parallel with 3 divided by 3 times IC, which is 2/3 IC. So in order to answer the question, we need to simplify this network to figure out what IC is. So the first thing I notice, if I have this 10-volt source, I have a 10 ohm resistor on the left-hand side. And on the right-hand side, I have 2 ohms, 4 ohms, and 6 in parallel with 3 gives me 2 ohms again. So now, if I want to find the current IC, I can do the current divider again, where IA is the current from the 10-volt source, and it divides to IB on the left and IC on the right. So IC would be equal to 2 plus 4 plus 2 in parallel with 10. So that's going to be 8 in parallel with 10 divided by 8 times IA. And IB would be 8 in parallel with 10 divided by 10, and that's IB. So now to write a voltage divider relationship. VD is the voltage across the 4 ohm resistor in series with the 6 and 3 ohm resistors in parallel. So if I wanted to find the voltage across the 4 ohm, the 3 ohm, and the 6 ohm resistors, I would use the voltage divider, where the voltage across the 4 ohm is equal to 4 over 4 plus 6 in parallel with 3 times VD, which simplifies to 2/3 VD. Since the 3 ohm and the 6 ohm are in parallel, they have the same voltage, which is going to be 3 in parallel with 6 divided by 4 plus 3 in parallel with 6 times VD, which equals 1 over 3 VD. In order to now solve for some numeric values, we have to find the equivalent circuit and solve for IA, which we'll do next. So now to confirm the law of conservation of energy, we can actually walk through this circuit using KCL and KVL, voltage and current divider. So the first thing you notice is that since I have a 10-volt source in parallel with a 10 ohm resistor, the current right here should be 10 divided by 10, which is 1 amp. And on the other side, since 2 plus 4 plus 6 in parallel with 3 gives me an 8 ohm resistor on this side, IC, which is the current on this side, should be 10 divided by 8, which is 1.25 amps. So when you sum those two together using KCL, that makes the current from the voltage source 2.25 amps. So this yields the current through all of the resistors except for the 6 ohm and the 3 ohm. So the current through the 6 ohm resistor should be 1/3 times 1.25, and the current through the 3 ohm resistor should be 2/3 times 1.25. So the current through the 6 ohm resistor is 0.417 amps, and the current through the 3 ohm resistor is 0.833 amps. So now let's find VD. First, VA. VA is equal to 2 times IC, which is 2.5 volts. VB is equal to 4 times IC, which is 5 volts. And based upon KVL, the sum of the voltages around that right loop have got to sum to 0, so that would mean that VC must also be 2.5 volts. Since VD is the sum of VB and VC, that's equal to 7.5 volts. So now that we have all of the elements on the circuit, let's check the power table. I make the columns, and then I write down all the elements. 10 volts, 10 ohms, 2 ohms, 4 ohms, 6 ohms, and 3 ohms. So the 10-volt source had a current of 2.25 amps, and it was the only element delivering power, so it's negative 22.5. The 10 ohm resistor had a voltage of 10 volts and a current of 1 amp, so it absorbs 10 watts. The 2 ohm resistor had a voltage of 2.5 volts and a current of 1.25 amps, so it absorbs 3.125 watts. The 4 ohm resistor has a voltage of 5 volts and a current of 1.25 amps, so it absorbs 6.25 watts. The 6 ohm resistor had a voltage of 2.5, a current of 0.417, so it absorbs 1.0425 watts. And the 3 ohm resistor also has a voltage of 2.5, a current of 0.833, and it absorbs 2.0825 watts. When you sum the power, that does indeed equal 0. This concludes our discussion of series and parallel resistances, as well as the voltage and current divider.